Hi everyone, today I present the paper Quality-Agnostic Deepfake Detection with Intra-model Collaborative Learning. The paper was presented in the ICCV 23 and I am Ben. So let me first introduce about my lab. My lab was led by Professor Simon Wolf, and there are 7 doctoral students and about 19 master students now. Our lab focuses on 3 topics: data-driven, with applied data science and data engineering, and satellite system data. Second one is the AI. It research about defect detection, time series anomaly, and outlier detection. Last one is privacy and security. It research about online user privacy, abuse and fake information detection, and machine learning with security and privacy. So more about information about our lab, you can visit this URL. So about the venue of this paper presented in ICCV 23 in Paris in last October, and ICCV is the top 3 conference in computer vision and pattern recognition, according to Google Scholar. So the outline of my presentation today is: first one, introduction. It present about the problem and motivation. Second one is our methods. Third one is experimental result, and the last one is conclusion. So the first problem is, as you may know, that deepfake have become popular in recent years and garnering significant attention. And the misuse of deepfake is you can see in every perspective of your life, including pornography, fake news, and still privacy information. So in 2019, Amazon, Facebook, and Microsoft have launched a competition about defect detection with total prize about $1 million in cargo. Also, in the same time, there is a lot of defect-based deep learning-based detection methods that have been proposed. It's including image classification, frequency analysis, temporal consistency, and audio-video consistency. However, there is problem is detection methods perform poorly on compressed video or image. And it's become a problem because every time you upload a video or image into social network, the provider usually have to compress your video or material to save the story. So to solve the problem, some studies have paid more attention to low-quality compressed defect detection. First one is in 2022, they proposed a super resolution network to increase the quality of input image. For example, this is a low quality, and after the super resolution network, it increase the quality and then it's put to the detection network. The second one is knowledge utilization approach in 2022 also. And for example here, the high quality image were retrained on a teacher network. And when you want to detect a low quality image, you have to train a student network, and the student network distills the knowledge from the high quality. However, both of the approaches have to be used different modality model for its quality, and it become impractical because you have to know the input, the right information of the input. So our motivation is that we have to build a unified model to detect defects from different quality modality. For example, here you have 3 modalities: RAW, C23, and C40. This is to codec video compression, and the AUC score here is the performance of the model on its quality. This is the baseline one, which means the reverse word. They can train the 3 modality in one model, and the performance is quite really good on 3 modality. Another approach is I presented in the last slide. They develop separate model for each modality. and it has a slightly improvement over the compression version of the data. However, there is still lower performance on the raw. And we want to develop a single model, which means similar to baseline one, but you have to collaborative the feature of each modality inside the model to enhance the performance of overall. And this is our performance after training, which increase the performance on 3 modality raw, C23 and C40. So our contribution in this work is we provide a theoretical proof about the classification error of low quality defect, and this classification error is bounded by the classification loss and the distance between its feature and the high quality image. Secondly, we design a network and training framework named Quality-Agnostic Defect Detection (QAD). We include the Hilbert-Smith independent criterion and the adversarial weight perturbation model to improve the performance on 3 modalities. And finally, we experiment with different datasets and show that our methods can show superior performance. So first, we go through the notation in this paper. Let's a raw sample and its compressed version at the quantile C is expressed at the SC equal to SR minus 2C. So SC is the compressed version and this is the raw version. We subtract to amount of information. And we have a training dataset D. And the learning network F is a mapping function from the input image to the output prediction. It's a binary prediction because you only have the real and the fake prediction. And the parameter of this network is theta. And we also have the loss function L. And we consider in this work is the submap function with the binary cross entropy loss. So our theorem is that for any network F with a probability of 1 minus delta over the raw of the dataset D, we have this inequality, and where RD is the Rademacher complexity and the LE collaborative is the distance between the raw image representation and compressed image representation. So let me go into detail of the theorem. So the theorem says that if we want to minimize the expectation error, we can minimize the classification loss and the collaborative loss. So the left term is the expectation error. The green term here is the classification loss. And the blue term here is the collaborative loss. So how we can do that? For the classification loss, we can apply the adversarial weight perturbation to robust the model to the input corruption. For the collaborative loss, we apply the Hilbert-Smith independent criterion to encourage geometrical similarity of the raw data and the compressed version. So let me go into detail. The overall training scheme is like this. For example, we have the input video. We can make it to raw and apply the codec compression. We develop at the same time for 2 models, but between them we share the weight, which means they only the one model, but forward for the top one, forward the high quality, for the bottom one, forward the low quality. And in the middle, we apply the Hilbert-Smith independent criterion here. At the output, we calculate the adversarial weight perturbation to improve the robustness of the model by lowering the loss landscape of the model. So let me go first into the AWP here. For example, this is the loss landscape of the model, and the theta at the training step is like this one. and this is the class 0, which means you can imagine this is the real image and this is the fake image. At the training step T, we're looking for the most direction that increase the loss value in the direction of phi within the radius of gamma, and we add in the phi star here into the theta. So phi star is the worst case perturbation of the model wave, and phi star can be generated by the adversarial methods in this formula. This means that you have to find the maximal vector that increase significantly the loss value between the reduction and the label. So you can imagine like that this way. Usually, if you want to increase the generalization of the model, you apply some argumentation into your data, like adding noise, rotation, or cropping your image. However, we don't know which type of argumentation called the severe degradation of accuracy in the training. And AWB, on the other hand, is can understood as a word argumentation for the model during training. But the AWB apply argumentation into the model ways instead of the data. And the AWB can guide the model to the flattened loss landscape. This means it's more robust to the input corruption. And in our problem, you can understand it as the compression image or compressed video. About the Hilbert-Smith independent criterion, for example, you have a midi-bag of high quality feature at the intermediate layer. This is the high quality and this is the low quality. And its feature its instance have the dimension of channel C, YW, and height of H, and B is the size of mini-bag. You can apply a kernel to calculate the distance between any instance in the high quality and form a distance metric like this one for the high quality and similarly for the low quality. And then we apply the Hilbert-Smith independent criterion. You might notice that why we don't apply covariance to measure the dependency between two variables. However, zero covariance does not mean two variables are independent, but Hilbert-Smith independent criterion so it's tractable computation and equivalency in terms of the dependent property. For the training scheme, for example, we have a mini-bag B include M quality modality. This is the raw image, this is the compressed level 1 and 2 compressed level M-1, and our end-to-end training objective can be seen as follow. This is the adversarial wave perturbation applied on the loss and calculate for every instant in this midi-bag. And second one, we calculate the collaborative, which means the geometrical similarity between each modality to another. In the experimental result, we use 7 datasets, which is very famous in the research community for defect detection. We also apply 2 compression versions with one time rate of 23 and 40, and we form 3 modalities, raw, C23 and C40. Meanwhile, we use 2 backbone, ERESNet 50 and EfficientNet B1. We name it as Quad R and Quad E. For the baseline, we have 8 baselines for compare with our methods. With the experiment quality-agnostic, the baseline model don't know the input quality. For example, this is the result on the video compression, and this is the result on random JPEG compression. As you can see, our methods show a superior performance on average compared to all of the prior methods. In the quality aware, the baseline model knows the input quality except for our methods. Here we comparing with the super resolution methods and knowledge distillation methods, which they know the real information, which means the input image is compressed or not, while our model doesn't require any information of the input, and it achieves the highest AUC score. In our application study, here we show different approach for the collaborative loss and adversarial loss. Also, we also study the impact of hyperparameter gamma and alpha, which is the way of this is the radius of the adversarial wave perturbation, and this is the way of the collaborative loss alpha. Also, we saw the Disney visualization of baseline versus our approach. For the baseline, you can see that the real raw and real compressed, as well as the fake and raw and fake compressed, is discussed everywhere. But when apply our approach, they are gathering in the same class, which is more condensed. In conclusion, in this paper, we propose a unified defect detection framework, QID, to solve the problem of quality-agnostic defect detection. And our proposed method helps show a competitive detection performance without the real knowledge of input quality. For more information, you can access to our paper here. And thank you for your listening.